Welcome, everyone. So this is the first session on homomorphic encryption. We will have 3 talks on the topic, and then 3 other talks later on for homomorphic encryption too. So the first talk will be on optimized homomorphic evaluation of Boolean functions. And it's a work of Nicolas Bon, David Poincheval, and Mathieu Rivin. And Nicolas will give the talk.
Thank you. So hello, everyone. I'm here to talk to you about fully homomorphic encryption, and more specifically, how to evaluate Boolean functions using fully homomorphic encryption. So as I'm the first speaker of the session, I thought it would be a good idea to introduce fully homomorphic encryption for those of you that are not familiar with it. And then I will introduce you to the TFHE crypto system. And finally, we'll talk about our contributions, so how you use TFHE to evaluate Boolean functions. So FHE, it stands for fully homomorphic encryption. And the typical use case is you have a client that has some data, and you have a server that has some application, so for example, a neural network. And the client wants to use the neural network on its data, but without revealing the data to the server. And so the idea with FHE is you encrypt the data with a homomorphic scheme, and the server runs a homomorphized version of the neural network, where the basic operations are replaced by the homomorphic counterpart of the operations in the clear text. And then all computation can be performed without decryption. So the client crafts an evaluation key here in green that allows you to do computation, but that does not allow you to decrypt. And then it sends the encrypted data and the evaluation key, and the server plugs the evaluation key into the homomorphic neural network, and then it can run the computation encrypted, get an encrypted result, and the clients can decrypt the result. So that's the nice theory. In practice, there are a few challenges to overcome before FHE become mainstream. So the first one, so you may have heard that FHE is really slow, and that's true. It has huge overhead in time and in memory. The other hard stuff with FHE is that so it's lattice-based, so there's noise in the ciphertext, and so when you do computation over noisy data, you get more noise, and so you need a mechanism to monitor the noise and to regulate it when it's too high. And finally, the crypto systems provides you a limited set of supported homomorphic operations, and so developing complex application is like hard, and so you need tools. We need tools to compile circuits and to compile applications to make development easier. So that was a fully homomorphic encryption, and now I'm going to introduce you the TFHE crypto system, which is one of the most promising schemes in the literature. So how does it work? It maps a clear space over an encrypted space, and the clear space is what we call a discretized torus, but we can just think about it as a ring, so a ring of P elements. And P has the size of a few bits, so in TFHE we manipulate small limbs of data, so basically 4, 5, 6 bits, and I'll explain later why. And then the ciphertext, they live in the encrypted space, which is a discretized torus as well, but here the discretization is much thinner, and it's something like a machine precision, so 32 bits, 64 bits, and so on. And so how you map the clear space into the encrypted space, there's a natural way of doing it, and it's just to slice the encrypted space into P slice. And if you want to encode a message of the plaintext space, you just pick the element in the middle of the sector corresponding in the encrypted space. And as I said, the scheme is noisy, and so you add a bit of noise, so a random Gaussian noise. And as you can see, if the noise is small, you do not lose correctness because you stay in the right sector. But if the noise becomes too big after too much computations, you go out the sector and you lose the correctness. And so to be completely full with how the encryption works, so this is standard LW encryption. So you sample n elements of the encrypted space, And to give an ID, n is about 500, 1000. And then you use the secret key, which is a binary vector. And to encrypt, you add a slot to the vector, and you put the scalar product between the mask and the secret key, and then you add your encoded message with the noise. And you get a ciphertext. So that's interesting, but what's really interesting with FHE, it's the operation you can do, the homomorphic operations. And so trivially, this scheme is linearly homomorphic, so you can do sums and you can do products by clear constants. And these operations are quite fast, but they add noise in the computation, in the ciphertext, sorry. So you cannot carry on forever with linear operations. At some point, you need a way to reduce the noise to not lose correctness. And in TFHE, this is done by the third operation, which is the programmable bootstrapping. That allows you to reset the noise level homomorphically, so that's nice. But what's extra nice is that while you are resetting the noise, you can evaluate any lookup table on the ciphertext. But it comes to the cost to a very slow operation. And so the typical workflow with TFHE is you want to pack as many linear operations that are super fast as you can, and when the noise becomes too big, you do a bootstrapping, and you have a fresh ciphertext to work with. And I told you at the beginning that we only work with small precision, and that's why. So this is the time that takes a PBS, so programmable bootstrapping, with respect to the precision of the plain text. And as you can see, the time explodes, the complexity explodes, and so you never want to bootstrap a too big ciphertext that is on a too big precision. And so that was the introduction to TFHE, and now how do we evaluate Boolean functions with TFHE? The natural approach, the first thing you think about, is to encrypt each bit in a ciphertext, and then you see the Boolean function as a Boolean circuit, and you say that each Boolean gate is a 2-input lookup table. So I told you that programmable bootstrapping was 1-input lookup table, but you can construct a 2-input lookup table simply by considering a 1-input lookup table, and you double the entry size. But the problem, of course, is that now you bootstrap every Boolean gate, so it does not scale at all when you want to evaluate large circuits. The other approach is like the complete opposite, and it's to pack every bit into a ciphertext of a much larger precision, and then to do one single lookup table. But the problem with that is that the programmable bootstrapping, it becomes very slow if you work with more than 5 or 6 inputs. So it does not scale either. And so that's where we are. We developed a framework that solved these two problems. And so the first question we need to ask is how do we represent a bit in TFHE? And the obvious solutions, you may say, is well, just take p equal 2, and the right-hand side is the bit 0, and the left-hand side is the bit 1. But the problem with this, that is that you do not have a 2-input lookup table, because you need to have some room to fit the second operand. And so actually, when you are working like this, the sum of TFHE becomes XOR, and that's pretty much all you can do. So you need a bit of room. And so what was done in the literature was to use plaintext modulus that is a power of 2. And so now you have plenty of room. But now you are facing what's called the negacyclicity problem. And I'm not going to enter into the detail, but what's happening is you have to choose the two fix. One is to accept that you cannot evaluate every function you want. You can only evaluate negacyclic functions, but that's really restrictive. And the other way around is to use a bit of padding. And when you use a bit of padding, you fix the most significant bit to 0. But now you don't have an homomorphic sum anymore, because when you are doing sums, well, sometimes you have a carry, and the carry propagates on the bit of padding, and the bit of padding is not 0 anymore, and so you lose the correctness. So that's not quite what we want, and so what we propose is to use a prime value for p, so a prime and so odd. And when you manipulate odd modulo, the negativity problem vanishes. And so that's what we formalize in the paper by the term p-encoding. And the p-encoding is simply the idea that you map a bit on a subset of the elements of the torus. So here, for example, if you decrypt a 2, you get a bit 0. And so with this formalism, the function evaluation becomes really simple, because now what you can do, you can sum the inputs that have specific p-encodings. And when you do a sum, you get a result that has different p-encodings. And once you have this intermediary result, either you decrypt and you get your result, and if you want to do more computation, you can just do a bootstrapping to reset the p-encoding and to do more and more other functions. So how does it work concretely? Let's take a toy example to explain it better. So let's say we have a Boolean function of 3 inputs that have these 3 p-encodings, and you take the truth table of f, and you look at what's happening in every case. And so if you take 0, 0, 0, you're going to sum the 3 red elements on the torus, you land on 5, and then you look what's actually the result of the function I want to evaluate. And if, let's say, it's 1, well, we label this sector in green. And you do that for every line. So each time you label an element. And of course, if you take random p-encodings without thinking too much, you're going to have some overlap in your result. And if you have an overlap, you lose correctness, because it means that some part of the torus are both the bit 0 and the bit 1. So that's nice, but how do you find the right p-encodings? So yeah, before, what's the advantages of the method? It solves the 2 problems of the previous approach, which is that you have one single bootstrapping to evaluate the whole function, and you don't need to extend the plain text space to fit more inputs, because all you're doing is doing a sum, and the sum is free. But so, as I said, how do you find the right p-encodings for a given function such that you don't have any overlap? So you cannot do an exhaustive search because this would explode, but we prove in the paper that you can restrict the search to p-encodings that have this form. So the bit 0 is mapped on the 0 element of the ring, and the bit 1 is on some other element, on some other singleton. And this is enough to find the most efficient solution. And so how do you solve that? Actually, if you come back to the problem and you change a bit your point of view, you can see that what we are constructing is some sort of linear system where the coefficients are the truth table. The right-hand side term is the resulting p-encodings, and the unknown are these di's, so these values for the bit 1 of the p-encodings. And so you construct this linear system, but the problem is that this linear system has 2 to the L lines, and for L unknowns, so it's super overdetermined, and you have a very low probability to get to the solution, but actually, you don't really care what does the result looks. You just need that to not have any overlap. So you just need that the red lines and the green lines are not equal to each other. And so if you rewrite this problem with this setting, you get some kind of linear system that is not actually a linear system, because you have differences, you have inequations, and you are modulus a prime number. But actually, this is really easy to solve with a simple recursive search, really basic, where you fix the first di, and then you have all the solutions for the second one. And then with the constraints of the system, you can cut the branches of the tree and so on and so forth. And if you can find a path of length L, you have found a solution. The thing is, this only works if you know the right P, but to identify relevant values for P, we developed an heuristic method that finds an upper bound on the optimal P, and we show that in the paper that this is pretty tight, actually, and that it's in general enough to find the optimal P. So this is some experimental results. So we tested our method on symmetric crypto primitives. So for use cases that includes transciphering. So transciphering is the idea of encrypting data using a symmetric scheme, doing the transfer with this one, and then evaluating the decryption algorithm in FHE to save bandwidth. You can construct also oblivious pseudo-random functions. You have plenty of nice construction you can do with FHE and symmetric primitives. And as you can see, we beat the state of the art for like Simon. So Simon is a lightweight block cipher, Ascon as well. Trivium is a stream cipher, and there's the well-known Ketchak hash function. And so this is the values of P for where you find solutions. So Ascon was pretty hard. And then we tried to do AES, but with AES we couldn't find any solution that was with satisfactory values for P. And so what we did is we leveraged circuit representation of the AES, and we developed heuristic to slice the circuit of the AES, and then apply this approach to every subcircuit. And so you can construct a library of gadgets. So what we call gadget is a solution to the problem that allows you to evaluate a subcircuit in one single bootstrapping. And then you can plug them into each other, and you can switch encodings really easily. So for the record, switching encoding with this method, when you have a prime number as a modulus, you can just do it using sums and a multiplication by constant. So the encoding switching are free. And so you can evaluate a large circuit. And so this is the performances we get for AES. So here again, we beat the state of the art at the time. Then the further work beat us afterwards and will be presented in this conference. But yeah, basically, the approach scaled pretty well for large circuit as well. So that's all for me. So basically, we developed a framework to evaluate Boolean function using FHE. And actually, the only change we did to the original scheme was to adapt the bootstrapping to remove the padding bit that you need when you have a power of 2 so we had to remove it because we were working with odd modulo. So this required a slight adaptation of the bootstrapping, but like nothing serious. And so this, in my opinion, this makes this tool a good tool to integrate in a larger compilation homomorphic toolchain, because it's conceptually quite simple, and it uses the TFHE component as building block without altering them also. So yeah, I'm happy to take questions.
So thank you for the talk, Nicolas. Do we have some question in the audience? In this case, you can go to the aisle.
Hi, thanks for the talk. So did I understand it correctly that for you had to find these encodings for a given circuit? Yep. Or could you also just take the parameter P and then could you generate a list of every possible function you can compute? Because you mentioned tool chains, right? And you kind of want to know what you maybe can translate high-level code into. So that's kind of what it's aiming at. Can you build a kind of gate library with this?
Yeah, that would be possible, I think. We could have done that for AES, actually. For AES, we handcrafted the slicing using some heuristic that are quite naive, to be honest. But probably, yeah, I think it's a good idea. But I guess it would have too much cases if you want to evaluate functions with more than 8 inputs. I guess that would completely explode. But for small values of P, maybe yeah, maybe it's a good idea.
All right, thanks.
Okay, so let's thank the speaker again. No, sorry, there is another question.
Thank you for the talk. And if I understand correctly, is there any possibility whether the P does not exist for maybe some circuits or and even for the longer circuits there do not exist the decompositions of the gadgets and the encodings to decompose the whole circuit.
Yeah, but in this case, you cut your subcircuit in half and you apply the approach to the two halves, right? I'm not sure I understood the question.
So my question was, at least for some smaller circuits,
yeah,
can we guarantee that the P, the number P, the
yeah.
prime P, and the encoding exists for all the circuits?
For all the circuits? Yeah, okay. I don't know.
Thank you.
Okay, so if there is no other question, we will go to the second talk. Let's thank the speaker. So,
is that the thing to switch the screen?
Yeah, it's this one, so green and red to go back.
Okay.
So this talk is on fast transciphering with batch and reconfigurable LUT evaluation. It's a work from Leonard Schild, Aisajan, Abidin, and Bart Renel, and Leonard will give the talk.
Yes. Thank you. So let's get started. Well, first we'll talk about some background, but the previous speaker already covered a lot of it. Then we'll look at previous methods to evaluate lookup tables homomorphically, and then we'll talk about our new algorithm. Okay, so background. So this you already heard on the last talk, so we'll quickly skip that. Though what we're now going to do is go a bit more into the details about what the previous speaker said. So if we have some LWE-based encryption, our secret key could also be treated instead of a mask as just a vector from this module up there, and messages just values between 0 and t. And ciphertexts are then just called learning with error samples. And to encrypt is, as we've seen before, so we'd sample a random vector, compute the inner product between a secret and this vector, add the message and the error. And to decrypt, we'd do the opposite. Though if you don't use this torus description, what you usually do is also scale the message. So you can, when you decrypt, round it and actually obtain the message again. And maybe something new is now so-called ring LWE-based encryption. And we can play a very similar game to the LWE case, though now we're going to encrypt polynomials. So pay attention to what's happening in red and top right. This time we'll work with a polynomial ring. And to encrypt values, we play almost the same game. So we'll sample a random polynomial, multiply it with the secret polynomial, add the scaled message polynomial, and an error. Now, what we'll have to pay attention to, again, because this is going to be a problem and something we'll use later, is that in our ring up here, we have x to the n is going to be congruent to -1. And so this negacyclicity problem the previous speaker mentioned, we'll come back to that in a second. But first, here was just a quick demo to actually see that ring LWE samples are also additively homomorphic by default, and also homomorphic with regards to scalar multiplication. And another new thing is that if you have a set of n LWE samples and want to pack them together, you can do that. And you can just pack them into the coefficients of a polynomial in a ring LWE sample. Right? Now, blind rotation. The previous speaker mentioned program bootstrapping, and to do this, the core operation is the blind rotation procedure. And so what it will take as an input is a polynomial, or actually a ring LWE sample encoding a polynomial, and a ciphertext. And it will compute the right-hand side there. How exactly, I'm not going to discuss, because there's a range of methods to do it. But we'll go over some special cases. I mean, if the modulus of the plain text was not equal to 2n, but just n, what you can see is we will have a random sign flip here. And again, this is due to the properties of a ring, where x to the n is congruent to -1. Likewise, if the ciphertext modulus was equal to 2n, this sign flip is no longer random, but will be more or less fully determined by the most significant bit of the decrypted ciphertext. And the power of the monomial will be the decrypted ciphertext modulo n. This is the setting. So now we can quickly look at previous methods to evaluate lookup tables homomorphically. Now, I assume that everyone knows what a lookup table is, so we won't spend too much time on that. So we have a multi-dimensional array and some indices you want to use to, well, evaluate the lookup table. But now these indices are going to be encrypted. So the question is, how do we proceed? Now, the first thing you can do is use a blind rotation procedure. So how do you do that? Well, what you're going to do is you're going to encode the index in such a way that the most significant bit of the decryption is 0. And when you then run the blind rotate procedure, you won't have a sign flip. So effectively, what you're doing is rotating the coefficients of a polynomial by an encrypted amount. And since we can transition between ring LW samples and LW samples, you can just extract a constant coefficient of this result, which again depends on the encrypted index. Now, if you want to circumvent this most significant bit requirement, you can use other methods. They're usually also called functional programmable bootstrapping. I've included references at the end. It's just a set of works dealing with this problem. So this is a single-digit case. More interestingly is, what do we do if we have multiple digits? So the primary work is from 2021. It was also published at CHES. And we'll look at the tree-based method. So I'm going to exemplify it by a, well, two-digit case. So first, what we're going to do is treat the lookup table as a matrix, as seen here. So the first step would be that we use the algorithm previously described for a single index on every row of this matrix. So what you'll see is we're going to rotate the columns by the first index. This will result in a set of ring LRE samples, which we can extract and combine the constant coefficients of into a single ring LBE sample, and then apply the blind rotation procedure again on this new ring LBE sample. And so the result will actually then just be in kind of the 0-0 slot. A more intuitive perspective in the n-dimensional case is you have a, well, n-dimensional tensor, and you rotate the coefficients along every dimension by a certain index. And then the result is in the, well, 0 slot. Now, this was basically the naive version of this algorithm. It's been improved significantly since then, but the shortcomings of this version is that you're going to need an exponential amount of blind rotations, well, exponential in the number of digits you have. Then, if your lookup table has multiple outputs, then you will need to run this once per output. And this method will also require that the most significant bit of the encrypted digits is 0. So the number of blind rotations, well, they can be reduced to some linear amount, but this can be costly, though there's also a talk later, I think today or tomorrow, showing how this can be made faster. All right. Finally, we can come to our work. So we will actually focus on a very specific setting. And in fact, what we're going to do is focus on a setting where the digits are in base 2, so they're bits, which is quite common if you're working with some circuit. And the lookup table is going to map U bits to U bits again, so as many inputs as outputs. And what we want is to obtain all outputs at once, while at the same time minimizing the number of blind rotate calls, because usually this is the bottleneck, though later on I'll briefly mention it, not in our case. First, we're going to briefly revisit functional bootstrapping. So suppose now that we have a single lookup table mapping from a plain text space with T entries to a bit. Now, to evaluate this, we can actually set this accumulated polynomial for the blind rotation to 1, so, well, just a scalar, and use a modulus equal to n. And if we now blind rotate it, we'll obtain a ring library sample just of this monomial. Well, the monomial to the power of the encrypted ciphertext. And since ring library samples are homomorphic with regards to scalar multiplication, we can multiply them by the polynomial encoding a lookup table, which effectively rotates the coefficients of the polynomial just homomorphically. And so, once again, the constant term contains the desired values. Now, why does this solution not have problems with sign flips? Well, this is okay. Because, well, we're scaling by q half, where q is our modulus. And then, well, q half is going to be approximately equal to minus q half. And since later on, when we decrypt, we round anyway to the closest multiple to q half, this is not really going to matter, because at most it's going to be off by 1. Okay? So based on this, we can actually already sketch the first part of the lookup table evaluation. The first step is, from all the indices we have, we're going to select a set of size omega and combine them into a single integer instead of individual bits. This can be done with, again, blind rotate, but I won't explain too much how. It's fairly simple. If you're interested, you can approach me later. And this will incorporate information about the first omega bits, but we still have u minus omega bits left. So what we do is we just go over every possible value for these remaining bits. And since this is something I sketched on the previous slide, we can just keep on multiplying by polynomials. We can evaluate every possible case. Okay? But then, well, we can pack them into ring library samples based on these bit values we assumed. But kind of the question now is, we still need to select the correct ones. So how do we do this? And this is actually fairly simple. I've sketched the identity up there, so assume we have some field. And if you look at the identity, it's basically a mux, but instead of having a 0, 1 selector, we have a minus 1, 1 selector. And maybe you can already see this. Well, the blind rotate procedure induces a sign flip based on the most significant bit of the encrypted index. But if we are working with bits, then this most significant bit will correspond to the, well, index bit itself. So if we actually have that this error term is greater than 0, then the most significant bit is truly equal to the encrypted bit. Now, this is not too bad of a requirement, because usually we bound the error, and so if it's, let's say, between minus c and c, we can just add c on top of it and shift it into something positive. So this is not a bad restriction. Okay? And then once we have this, we can quite honestly just reproduce the identity above and compute, well, the sum of two ring library samples plus the blind rotation of the difference, and this will be approximately equal to, well, the ring library sample corresponding to the bit. Now I wrote approximately equal. Well, this is due because there's still some error in the decryption. So what is done in practice is you're going to pad the polynomials with certain, like, by repeating the values so that the error can kind of be ignored, right? And this is already the entire algorithm. So again, we generate all possible outputs based on the first omega bits, and the second stage, we select the correct subset of that. So what are the theoretical advantages of all of this? Well, no matter how many binary lookup tables we have, the first two steps only need to be done once. Otherwise, you just keep on multiplying by polynomials, which compared to everything else is very cheap. And if the number of digits is less than 10, then in fact, in our case, it's going to be very easy to find parameters with very high success rate, and which only have a linear amount of blind rotations necessary, as opposed to either exponential or some linear amount. And this initial composition stage of bits can be very easily parallelized. They're completely independent. So there's a lot of opportunities for this as well. And, oh, this is something I skipped. But basically, the optimization that can make the previous paper only use a linear amount of blind rotations can also be used in our case for well, the selection stage where we compute this mux. With that being said, asymptotically, so if we have more than U bits, most likely we will still need an exponential amount of blind rotations as opposed to the talk by the previous speaker. Right, so then what are the results in practice? We implement all of this in the OpenFHE library, which I recommend, and also do transciphering with regards to AES, with specifically AES 128, 10 rounds. We use the lookup table algorithm for the S-box evaluation, since everything else can be just done with XOR operations. And yeah, the timings are here. And this is something I mentioned earlier. The primary bottleneck is no longer the blind rotations themselves, but the repeated packing you need. So often we go between LW samples and ring LW samples. In practice, this is the bottleneck. All right, and then summarizing, we have a novel homomorphic LUT evaluation of binary digits. We actually work with the sign flips, so we don't really try to circumvent them. Speed up ranges anywhere from 1.5 to 4 times compared to other recent works. Though I will be the first one to say this is to be taken with a grain of salt, because most works use different libraries. So for example, I use OpenFHE. Other people use the original TFHE implementation, then there's Concrete, TFHE PP, etc. So it's all a bit difficult to compare, so I don't want to say, oh, who's the best. And specifically for my work, or our work, we can obtain bigger speedups by using GPU acceleration for the LWE to ring LWE packing, because at least the default methods very much resembles matrix vector multiplication. Otherwise, thank you for your attention. And if you have any questions, let me know. And here are also the references I mentioned throughout the paper. Thanks.
Thank you for the talk. So, do we have some questions in the room?
Thanks for the talk. So just one clarification. So here, when you are saying the LUT evaluation, that means you are, like for AES, you are considering the S box, right? The root of the S box.
Yeah.
Like, I mean, what can happen? So if I have any cipher, then that can be implemented in FPGA, right? FPGA usually lookup table, one of the unit, right? So typically, for example, a 6-bit lookup table, right? So then one can actually take the FPGA implementation and do the bootstrapping for the lookup table, like using that instead of viewing S-box as a lookup table. Just take the FPGA implementation, do some, exploiting the properties of the implementation, and get lookup table and then evaluate them, right? So that may be another way. Just but you used S-boxes, right?
Yeah.
S-boxes as a lookup table.
Yeah.
So, and another quick clarification. Another quick question is for AES, you have a same S-box, because my question actually came from, but because if I have multiple lookup tables, so will there be any dedicated bootstrapping for different lookup tables, or it's the same algorithm?
It's going to be the same algorithm.
It's the same algorithm. Okay.
Yeah, like you might need to modify the polynomials to multiply with, which I mentioned, but otherwise it's the same.
It's same generic. Okay. Okay. Thanks.
Anyone else?
Okay, so maybe one for me. Did you try to evaluate other transcipherings that with AES, like maybe a dedicated cipher for HHE? Or?
No, not really.
Okay.
Otherwise, we just focus on a LUT evaluation itself, lookup table evaluation itself. Just AES transciphering was just one application.
Okay. Okay.
Okay.
Well, yeah, if there is no more question in the room, I think we can thank the speaker again. And the third talk will be online, I think. So.
Hello everyone, I am Anisha Mukherjee. Thank you so much for joining me in the presentation of our work titled ModHE, Modular Homomorphic Encryption Using Module Lattices. This is a joint work between the Graz University of Technology in Austria and the Samsung Advanced Institute of Technology in South Korea. Today, I will give a brief introduction to homomorphic encryption, the use of ring learning with errors problem or the RLWE problem in homomorphic encryption and its challenges. Then I will move on to talk about our approach of designing a homomorphic encryption scheme using module LWE, the various potentials of such a scheme, the limitations, and finally the hardware aspects of it. To begin with, what is homomorphic encryption? It is a procedure that allows functional evaluation on encrypted data and hence preserves the privacy of data owners in outsourced computations. For example, if a hospital wants to outsource a patient's diagnosis, it can do so securely by encrypting the patient's sensitive data and then sending it to a research lab. The research lab can then perform homomorphic evaluations on the encrypted patient's data, send the encrypted diagnosis, back to the hospital, and then the hospital can securely decrypt it to let the patient know about their diagnosis. In this entire process, the outsourced computation to the research lab does not reveal any sensitive patient data to the lab, and this is the concept of homomorphic encryption. So the first fully homomorphic encryption came out when Gentry introduced the concept of fully homomorphic encryption in 2009, and this led to a plethora of lattice-based homomorphic encryption schemes. We got the first, second, third, and fourth generations of lattice-based homomorphic encryption schemes such as BGV, BFV, few-like schemes, TFHE, CKKS, and so on. And all of these schemes were based on some version of the learning with errors problem. For example, the ring learning with errors problem or the torus learning with errors problem, and so on. Now, what's the catch with homomorphic encryption? It is that computations in the homomorphic domain are several orders of magnitude more intensive than in the plain text domain, and hence hardware acceleration works have come up as a solution to bridge this gap in computational complexity. We saw a large number of works on hardware acceleration of CKKS, TFHE, BGB, and so on. Now, let's talk a little bit about what is ring learning with errors problem and how it's used in homomorphic encryption. The ring learning with errors problem tells us that mathematically it is hard to get to know the secret polynomial S with only the knowledge of the polynomials A and P. Usually in ring learning with errors problem based homomorphic encryption schemes, the parameters are the degree of the polynomial or the ring degree, that is the number of coefficients that are there in the polynomial, and the ciphertext modulus Q. For example, n can be 2 raised to the power 14 and q can be 400 bits and so on. So what are the challenges with RLWE based homomorphic encryption? The first is that there are many large polynomial arithmetic operations that have to be performed over and over again. And the second is obviously that different privacy preserving applications require different parameter sets based on their functionality. Now, to give you an idea of how big the FHE parameters are, this graph shows you a comparison between the parameter sets in post-quantum cryptography compared to FHE, which you can see are very huge. On your right, you can see another example of a table taken from the Homomorphic Encryption Standards webpage, and here you can see that to obtain 128 bits of security, you need at least 2 raised to the power 13 or 2 raised to the power 14 degree polynomials for modulus size of 200 or 400 bits. Now, what is the problem here? To understand the problems with RLWE based HE, consider this example where a cloud server is running an application that requires the parameter 2 raised to the power 13 degree polynomial and say a modulus size of 200 bits. Now, in order to run the application efficiently, consider a hardware designer who has spent months to tailor the hardware to work with these fixed parameter sizes so that the application can run efficiently. However, let's say in a few months, the application wants to now support more functionality, and hence the parameters have been changed to higher degree polynomial, which is 2 raised to the power 14, and also modulus twice the size, which is almost around 400 bits. But now the designer is not very happy. Why? Because the problem with hardware accelerators is that once they are manufactured, they are optimized for a certain fixed parameter size, right? In software codes, it is easy to change parameters. You can only change like a global parameter side, and then that changes the parameter in the entire code. But in hardware, once a hardware is manufactured, it is inflexible. It is fixed, optimized for a certain parameter size, and that makes the hardware designer unhappy. So this was our research question. We set out to answer the question that can we design a homomorphic encryption scheme that allows the same hardware to support multiple parameters N and Q for various applications efficiently. So what we realized is that we can use the module learning with errors problem to design a homomorphic encryption scheme. To give you an idea, continuing with the previous example, the application can now still run with 2 raised to the power 13 degree polynomials, but to support a 2 raised to the power 14 degree polynomial, what the designer has to do is that she has to instantiate two hardware units that work with 2 raised to the power 30 degree polynomials, such that finally you can still work with 2 raised to the power 14 degree polynomials, and hence she is now happy that she doesn't have to do any extra work other than instantiating more of the same hardware units. So this was our idea, and to give you a brief introduction to module LWE mathematically, it uses the same hardness logic as the RLWE problem. However, here we have to deal with vectors and matrices of polynomials, and the number of polynomials that we have to deal with within these vectors and matrices are determined by the module rank R. So continuing with the previous example, if we want to achieve a lattice dimension of 2 raised to the power 14, we can fix the ring degree to be 2 raised to the power 13 and use two polynomials of 2 raised to the power 13 degree to obtain 2 raised to the power 14 degree. Pictorially, this is how you can imagine. So instead of one big polynomial of 2 raised to the power 14, we have two polynomials of 2 raised to the power 13 degree each. Okay, so when we designed a homomorphic encryption scheme based on the module learning with errors problem, we named it mod HE, and we wanted to work with the synergies between RLWE and the MLWE problem, because at the end we wanted to achieve hardware usability, right? So we wanted our algorithms of the module LWE HE scheme or mod HE to closely follow the RLWE setting. So starting with, let's say, the homomorphic addition, it is a linear function and hence it's easy to mimic. For example, in the ring setting, if you add two ciphertexts, you again obtain a new ciphertext which consists of two polynomials, let's say of 2 raised to the power 14 degree each. And usually in RLWE HE schemes, we use the residue number system to split the big ciphertext modulars into smaller moduli, and this is like a layer of flexibility that RLWE has. In the module setting, addition is quite similar, but yeah, now we have to deal with a vector of two polynomials of 2 raised to the power 13 degree. But the good part here that we must remember is that module provides us an extra added layer of flexibility, because now we can split the ciphertext modulus obviously using RNS, but now we can also split the polynomial degree using a module. In homomorphic multiplications, things become a bit more complicated. In the ring setting, a multiplied ciphertext consists of three polynomials, out of which D2 is the nonlinear term with respect to S square, which has to be linearized. In the module setting, we have more nonlinear components, which are D2 and D3, and they are now vectors of polynomials. So to give you an idea of how the linearization is different in the ring and the module setting, in ring you always deal with one nonlinear component. In the module setting, you have more nonlinear components. So let's recall how a multiplied ciphertext can be decrypted in the ring setting. So a multiplied ciphertext can be decrypted using 1s and s square. So D2 is a nonlinear term with respect to S square, which we relinearize using evaluation keys, such that finally we obtain a new ciphertext consisting of D0 double prime and D1 double prime, which can again be decrypted using 1 and S. In the module setting, the decryption equation is quite similar. The only difference now is that the secret vector is a vector of polynomials. So when two ciphertexts are multiplied, the secret vector is also intrinsically multiplied. Hence, What we get are S square terms which result from multiplying the same polynomials, but also terms of the form Si and Sj which result from the product of polynomials among each other. So this is why we have more nonlinear components D2 and D3. Thus, to linearize them, we need more evaluation keys, and that brings us to one limitation of a module homomorphic encryption scheme, which we identified, which was that we need more number of linearization keys. Actually, the number of linearization keys increased quadratically with respect to the rank of the module, which was not the case in RLWE based HE. However, looking into the brighter side, we also identified quite a few potentials of an MLWE based HE scheme. So first of all is obviously better security assumptions. For example, so much literature is available on Kyber and dilithium, and the same security assumptions can also be held true for an MLWE based homomorphic encryption scheme, because MLWE interpolates between LWE and RLWE, and many structural attacks that work for RLWE do not work good for MLWE. Moving further, the second potential is hardware usability and more scope of optimization. So obviously, as I mentioned before, software is more parameterizable but slow. Hardware is very fast but inflexible. However, using mod HE or any MLWE based homomorphic encryption scheme, the same hardware that has been optimized for a certain ring size or ring parameters can be reused or instantiated r number of times to work for a module setting. Going back and recalling the example of a server and the application, we recall that the hardware designer is now happy because she can instantiate 2 times of the same hardware unit that works for ring to also work for module. Okay, so the third potential is increased scope of parallel computations. So if we go back to the linearization equation in the module setting, we said that there are more components to be linearized, and this was thought of as a limitation. However, this is not a bug but a feature, because consider this example where we work with a module rank of 2. So we have to linearize 2 polynomials d20, d21 with respect to d2, and 1 polynomial d3 with respect to d3. So this can be done parallelly using 3 parallel accelerators, where we require minimum interaction between these polynomials to actually linearize them. To give you a better idea, consider 3 parallel accelerators. What we can do is that we can provide the 3 nonlinear polynomials d20, d21 and d3, and ask these accelerators to parallelly linearize them. And here you see that these polynomials are of smaller degree. So that means the accelerators have to perform smaller computations, and only at the end there is a linear communication complexity where, let's say, accelerator 2 and accelerator 3 send their results to accelerator 1, who then accumulates all the result to finally give us the linearized components. So in the module setting, accelerators can work parallelly with smaller polynomials, which is a big win. The fourth is a feature which we found in MLWE schemes, which is ciphertext compression due to rank reduction. So consider this example where we start with a fixed ring degree, which is say 2 raised to the power 13, and based on an application we choose the module rank to be 4. So finally we have a full polynomial degree of 2 raised to the power 15. So the ciphertext now has 4 polynomials of 2 raised to the power 13 degree each. Now after performing several multiplications, let's say, the ciphertext modulus shrinks. So from 800 bits, the ciphertext modulus comes down to 400 bits. Now, with respect to 400-bit modulus, we can work with a ring degree of 2 raised to the power 14 as well. So we don't actually need 4 polynomials in our ciphertext. We can also work with 2 polynomials. How can we do that in the module setting? We just perform a rank reduction, which can be thought of a form of key switching. such that dynamically, when the application works, we can reduce the size of the ciphertext by reducing the number of polynomials within it. So from a rank 4, we go down to a rank of 2. Again, consider the application performs certain homomorphic multiplications or evaluations. Finally, we can also come down to the ring setting, which means we only work with one polynomial. So you see that the ciphertext can be the size of the ciphertext can be reduced from 4 to 2 to just 1 using rank reduction, which is like a very flexible feature that we found in ModHE. And to again talk about the hardware aspects, how all of these potentials translate into hardware, consider the case where we have a hardware accelerator that works for ring parameters. Like I said before, they can be instantiated r number of times to work for a module HE scheme, because as you must have realized from all that I've talked before, that that operations between module components are actually individual ring operations that just keep happening over and over again. So that is what we tried to also showcase in our proof of concept implementation, where, for example, if you have a application parameter big N and Q and you want to instantiate a MLWE based processor, what you need to do is you need to choose a rank R with respect to big N, and then you need to instantiate R number of RLWE processors which work with a fixed ring degree N, and you get an MLWE processor to work for your application. And as a proof of concept, in our paper we used a work which was published in CHES 2023, Medha, which is a ring accelerator, and we showcase that we can use Medha to also work for our ModHE scheme. So the concluding remarks, what are the key takeaways from such a scheme? That even though, as you must have realized throughout the talk, that in the ModHE scheme, we need to perform more computations compared to ring HE, and hence the computations are slow. And also there are more memory requirements because of the increase in the number of renderization keys and key switching keys. However, an MLWE based HE scheme provides immense parameter flexibility and hence allows reusability of hardware architectures. Also, it provides many parallel processing opportunities such that an accelerator has to work with smaller individual components. And finally, as looking out into the future, we plan to extend an MLWE based version for the different homomorphic encryption schemes such as BGV, BFV, TFHE, and so on. We also plan to look into the drawbacks of the scheme and try to overcome them so that the potential of an MLWE based scheme can be realized further. Thank you so much for listening to this talk, and I'm happy to answer any question that you might have. Thank you.
So Anisha is online, so if there are some questions, I guess we can connect with her. Or I can type them. So, yeah. Yeah, I think you can talk in the mic and she can hear. She's connected on the Zoom.
Hi, thanks for the talk. Did you look at all into bootstrapping, just any variant? Like you mentioned TFHE, BGV, CHES, but like, have you done any initial work on this so far?
So, can we unmute her? Like she is connected and I just see it. I'm asking if she heard the question. So the answer, yes, they have some of the bootstrapping algorithms, but it's an ongoing work.
I meant kind of, you mentioned that there's going to be changes in how expensive, for example, multiplication is. But then how would bootstrapping a ring LWE-based FFG scheme compare to this module LWE-based one?
So bootstrapping includes low-level functions that also ring operations. Yeah, okay, I think the typing to answer will not work, so I think it's better if this question are taken offline later on. Sorry. So let's thank Anisha again and all the speakers of the session.